Hello everybody, today we're gonna discuss about Ridge and Lasso Regression. In the previous tutorial we tried to discuss about polynomial regression, quantile regression, logistic regression, as well as linear regression. Today we'll continue the remaining types of regression, but for sake of this tutorial we only focus on the Ridge and Lasso regression. And this type of regression, that means Ridge and Lasso regression, is used when we faced a multi-collinearity problem in our data set. As all of you know that multi-collinearity occurs when dependent variables in a regression model are correlated. And this correlation creates a problem because independent variables should be independent. And if the degree of correlation between variables is high enough, it can cause a serious problem when we fit our model and when we interpret the result. Frankly speaking, multicollinearity may or may not be a problem. That depends on the purpose of our analysis and the extent of the multicollinearity. That means small to moderate amount of multicollinearity are usually not a problem, but extremely strong multicollinearity will always be a problem and may cause a serious error. And for example, if your purpose is primarily to predict or forecast the dependent variable, so strong multicollinearity may not be a problem because a careful multiple regression program can still produce the best prediction or the best forecast for the dependent variable based on all the predictor or independent variables. And the presence of multicollinearity in our data affects two things. The first one is the regression coefficient, and the second one is the p-value. But multicollinearity doesn't affect the goodness of its statistics or the overall model significance. So there are a number of ways that can fix the multicollinearity problem. The first one is just very simple, dropping some of the correlated predictors, and the second one is try to standardize the independent variable or the predictor by subtracting their mean from each observation. So we can directly use this standardized value in our analysis or in our model. And the third one is obvious, it's very simple, doing some linear transformation. And the last, I mean the fourth possible solution for the problem of multicollinearity is carrying out analysis using Ridge, Lasso, as well as the principal component regression. So today we'll only focus on the Ridge and the Lasso regression. So you may ask me how do we know whether the multicollinearity present or not. So there are three methods. I will show you how to check multicollinearity problem in your data set. So the first technique is using the correlation matrix. So the second one is using the VIF, that means the variance inflation factor, and as well as the tolerance. Then the third one is using the eigenvalues and the condition indices. So let's use some data which is found in our software. In order to do that, you have to use this incorporated reverse package for the data manipulation, and we will use the MTCars as example to check the multicollinearity problem. So type this, and from all observations that found in this data, let's select only 5 variables: 1, 2, 3, 4, and 5. So type this and submit to our studio. In case if you want to see the first observation, so type this and submit to our studio, you can get this information. So here is our variables. Here is our variables. So we will check multicollinearity problem on this data set. Then the first one is using the correlation matrix. In order to do that, the core plot package is mandatory. Then use the core plot function under parenthesis core. So the correlation of data, or data is what you will get. We will get a correlation of all these variables. So type this and submit to RStudio. So you'll get made in the right side bottom corner of our RStudio. So to say multicollinearity, the value below negative 0.9 and the value above positive 0.9 will consider um, as a multicollinearity. For example, in this case, here is this one is a problem with this one, and again this with this one. I think more or less they are similar. So the two variables are highly correlated. So there is a presence of what? Multicollinearity. Then the second one is the tolerance and variance inflation factor. In order to do that, first we have to create the regression model. So in this way, I assigned rig, but you can give any name that you want. Then linear model. Then this MAPG, that means from the 5 observation, I considered the MAPG as the response variable or dependent variable, and it's explained by the remaining variables. So I created this model. Then if you want to get the summary, you can carry on, but that's not my objective. Then in order to get both the tolerance as well as the variance inflation factor, we have to use the OLS VIF tolerance. But this function is built on this package, so you have to install it if you haven't this package, or you have to run if you have this package into your software. Then OLS, then here is the variance inflation factor, here is the tolerance. So then you have to indicate the model. So our model name it here is rig. Maybe it's differ for you. Maybe it's your name, maybe other things. So, but in our cases, the regression model is rig. So you have to provide this model into this parenthesis. So type this and send it to RStudio. So when we get, that means if we get the tolerance less than 0.1 and the VIF, that means the variance inflation factor, above 10, we will consider that there is a presence of what? Multicollinearity. So coming to our result, this one, that means 0.09, which is less than 0.1. And again, when we compare the variance inflation factor, here is greater than 10. So yes, there is a presence of what? Multicollinearity. And the third one is using the eigenvalues and the condition indices. So in order to do this, also this package is mandatory, and you have to use OLS again. That means the condition index. So this will work with a combination of large proportion of variance. That means if you get the variance 0.5 and above with condition number 10 up to 30, so we'll consider there is a presence of multicollinearity. Then again, you have to provide your regression model in the parentheses. So type this and submit to RStudio. As you can see that there are two values that are between 10 and 30 for the condition index. So let's see that. Here is 19.14 and 26 are in the range between 10 and 30. Then this is not only the possible way, but we have to combine this means the condition index with large proportion of variance. To say that large proportion of variance, the value should be equal to 0.05 and above. So let's see on the four variables. In this case, it's not, because it's less than 0.5, less than 0.5, less than 0.5. Yeah, here is 0.6. So this is one problem. Again, let's see for the 26. So this is intercept, so don't deal on this. Yeah, here is greater than 0.5, since the value is 0.67, and again is 0.76. So these two parameters are a problem again, but the remaining variables for HEP and the WT, the value is less than 0.05. So we get three variables here in this WT. Again, here is the CYL, and here is DSP, because on the basis of this criteria, with high condition index, with a combination of large portions of variance, will considered as multi-collinearity. So by this way, you can check the multi-collinearity problem in your data. So let's back today's tutorial. That means the ridge regression. And this regression is used when we face the problem of multicollinearity in our dataset. And that means this type of regression is an extension of linear regression, where the loss of function is modified to minimize the complexity of the model. And this modification is done by adding a penalty parameter that is equivalent to the square root of the magnitude of the coefficient. So in order to do this regression, we must use the Gelminate package. So you have to incorporate this package into our software, and let's import our data. Then our data is in the form of Excel, then it's from the desktop. Yeah. So let's type RR. Yeah. So our data is contain a number of observations, starting from total tiller and with the hectoliter weight, which is the wheat data, and which is conducted in different locations and using different types of blended fertilizer. So the first step is getting of the independent variable. So in order to do that, we have to use the data matrix function. Then you have to indicate your data name. In our case, RR is our data name, and we will select this parameter 1, 2, 3, 4 parameters as independent variable or predictors. Then again, let's submit this one. Again, we have to get our dependent variable. So dv is equals to I assign gradient as dependent variable. Then you have to set a number of lambda values that ranges from 10 raised square means 100, then minus 2 means equal to 0.00, that means 10 raised minus 2. Then there get a number of ranges, that means by reducing 0.1. For example, 10 to the power of 2, which is 100, then 10 to the power of 2 reduced by 0.9 means 10 to the power of 1.9. So in similar fashion for the negative 2. So type this and submit to our studio. And the reason why we do this is to get a number of lambda values. So let's see these lambda sequences. Then finally we will select the best lambda and will fit our model. So these are the ranges that are created by this formula. Then after we can build our regression, especially ridge regression. So assign any names that you want, and you have to use the glmnet function here, and independent variables comes first, then followed by dependent variable, and you have to set alpha is equals to 0. So alpha is equals to 0 means it's a ridge regression, but if you provide alpha is equals to 1, it will be lasso regression. Then you have to indicate lambda is equals to the lambda sequence. So type this and submit to our studio. Then you can get the summary, of what your model means work. So in this way you will get the summary of your model. Then after we can choose the optimal lambda value using the different cross validation, using the cross validation element. So you can give any names that you want here. I just assign here is regression cross validation, and you have to use cv.gelnet function, and this followed by independent variable, then dependent variable, then alpha is equals to 0, then the lambda sequence. As you can see, there are a number of lambda sequences. These are all lambda sequences. So the cross validation helps to select the best one from these lambda values or lambda sequences. Then type this and submit to RStudio. Then how to select the best or the optimal lambda value? So to do that, you assign any name that you want here, but I just assign here is best lambda value. So then the RCV is what we created here. Then select the minimum. The min means will help you to select the best lambda value for our model. So type this and submit to RStudio. Then we can see which is the best value of lambda. So according to this model, this function, it provides us 0.25 is the best the best lambda value. So we have to rebuild your model using the best or the optimal lambda value. That means 0.2511886. So the best ridge regression for our data is using the gelnet function, the independent variable followed by dependent variable. Alpha is equals to 0, then lambda is equals to what? This value. That means 0.2511886, or it's equivalent to the best lambda. So type this and submit to RStudio, then you will get your model. So how to get the coefficient? So you have to use the COE function, then the best ridge. So you will get the coefficient for the response for the variables. Yeah, here is the predictor variables. So by this way, you can get the lasso regression analysis in our software. Lastly, the lasso regression. The lasso is just stands for the least absolute shrinkage and selection operator, and it's also the modification of linear regression. And in this types of regression, that means the lasso regression is modified to minimize the complexity of the model by limiting the sum of absolute value of the model coefficient. So all procedures are similar to the ridge regression. What makes differ is alpha is equals to 1. So you can select the cross validation for the lasso regression, which helps to select the best lambda value. So type this and submit to RStudio. Then again, we find the best lambda value using especially the lambda mean. So type this and submit to RStudio. Then we will get our lambda value, which is 0.06. But in the previous we find the lambda value, especially I think it's 0.25 in the ridge regression, yeah. So but here is in the lambda 2 we get the 0.06. So this is the best for the lasso regression for our data. Then you can assign here is a WAG2. The previous one for regression is WAG, then independent variable followed by dependent variable. Alpha is equals to 1, but the previous one is 0. So lambda is best lambda value, that means 0.06202964. So type this and submit to RStudio. Then we'll get our coefficient using the COEF WAG2. So these are our coefficients. So by this way we can carry out the lasso and regression in our software. So thank you for watching, and if you have any question regarding to my tutorial, you can address me through my email, through my YouTube comment box, or through my email address. Have a nice time.